third grade, we made snowflakes. It was really fun. For some reason, we don't still. I'm not sure why. I'm bitter. So what we're going to do is pretend like you have a piece of paper like this, and cut out a piece right out of the middle. Okay? And so I have say, now this, and this. Now we can sort of do this two different ways. So you're going to have to sort of tell me which one you like better. So we could glue back in a piece like this, and then cut out a piece in the middle of it like that. And it'd make kind of a cool shape that zooms in like that. So that's option A. Or, this is kind of like a choose your own adventure. Except that you don't have to write a book before. It's different. Okay, or we can take this and we can cut out other shapes. I can cut out triangles out of the center of all of those shapes. And then, of course, cut out more and more and more. By the way, both of these are instances of fractals. Fractals is an infinitely repeating pattern as you zoom in. So which do you like better?
I've seen this one before. I've never seen the first one before.
Okay. Well, let's do the first one. So, here we go. We have a beautiful shape like this. What should happen? But Jennifer should cut a triangle right out of the middle. Now, Brenna has a little bit of sadness. You've just cut out that. But luckily, Brenna has a glue stick. So Brenna decides to glue back in a triangle in the middle that connects the middle there, the middle there, the middle there. Well, so that's all well and good. But then Jennifer comes back, and she doesn't like having that sort of upward triangle. So she wants to still cut out, she still wants a downward triangle cut out in the middle. So that still hurts Brenna's heart. So Brenna comes back and says, well, you can do whatever you want on the outside, but right in the middle, I'd really like an upward triangle. Jennifer doesn't want to tell Brenna that she's just wrong, so she's going to leave her triangle, but she's still going to cut out a hole in the middle because you can't really stick your finger in it and spin it around and go, whee, unless there's a hole in it. Well, this pattern goes on and on forever. However, Edgar, being very boring, only cares about how much area of paper is actually there. So we need to help poor little Edgar. Okay, so how shall we begin? Let's pretend, just for the fun of it, that this side down here is length 2. This side is length 2. That side is length 2. And that all these triangles are equilateral. Which we'll pretend I spelled right, just for the sake of argument. Okay, so before we cut anything out of it, how big was our shape?
4 times 4 divided by 2. So is it 2 squared, whatever the
So the thought is the initial area is 4 times 4?
Yeah, divided by 2.
4 times 4 divided by 2. So that's like
8.
16 over 2.
Isn't that the area of the triangle? Length times width divided by
1/2 base times height.
You're right.
Okay, so triangles area is 1/2 base times height.
Yeah, the height is where I went wrong.
So
Yeah, we don't know how tall it is.
What's the base?
2.
Base is 2.
So
Okay.
can you use Pythagorean?
So we've got 1/2
Yeah.
times 2. Then the height, I guess the height is right there. How am I going to figure out what the height is?
That's a right triangle.
It's a right
So
triangle.
we can use Pythagorean theorem.
Okay.
We know we have a
How
length of 2 and a length of 1.
Okay, so this side is
Yeah,
length
length
2, that
2,
side's
length
length
1.
1. I'd really like to know this height h. And so the Pythagorean theorem, of course, is a squared plus b squared equals c squared. And you're telling me that a is
1,
1, b is
x. No,
2 squared.
2.
So where is the a and the b usually?
Isn't C the hypotenuse and A and B are the legs?
Okay, so
Mhm.
the longest side has to be on a side by itself. Okay, so that makes this, I wrote an h here just to remind us that it's the height. You could use an x as well.
Okay.
Okay, and c is
2 squared.
2 squared. Okay, so we have 1 squared, which is 1, h squared, which is h squared, 4. We'll subtract 1 from both sides, so h squared equals 3. So h is the square root of 3. By the way, in high school geometry, it turns out that 90% of the time you only ever deal with 3 triangles. Okay? One of them is the 45-degree right triangle. One of them is the 30, 60, 90 right triangle. Incidentally, this was a 60-degree angle, so that's a 30-degree angle. This is 30, 60, 90. And the third one's the 3, 4, 5 right triangle. So if you get familiar with these, really, that's sort of where all those examples, now sometimes they're sort of hidden, shifted off the origin, but it's always those triangles. So that's where we start. Now, this piece is cut out. How do we figure out how much is cut out?
Couldn't you just take the area and divide it by 4? Since you
Okay.
have 4 triangles,
Okay.
and then you could subtract one of the triangles.
So Jennifer is saying that we have this area, and we take that area and we divide it by 4, and that gives us
1 shade of time.
this piece in here. Okay? So what do I do with that?
Subtract it from the initial area. No. No, then that's your area. One triangle, right?
Okay, so the area of one triangle is this 1/4, and you're saying that to get the remaining area after cutting out this middle piece,
Multiply by 3.
multiply by 3. Okay, so we've got 2 answers. One is subtract this from the original area, and one is multiply that by 3.
Can't you just take the area that we know and multiply it by 0.75?
Yeah. But isn't it valid to take away 1/4 of the area?
It's equally as valid.
Oh, it's
But I
equally
like-
as valid.
I like
Well,
positive
okay,
operations.
that's good. But it's important, particularly when you're working with students, particularly in the middle school years, that if somebody comes up with something off the wall, and I'll try to practice what I preach, and if I happen to get overwhelmed, then I'll say, no, you're wrong, you're worthless as a person. No, but you know, one of the challenges is when somebody comes up with something that's right, but not kind of the way you want to do it, not to belittle them, tell them they're born from an elephant. So I think the first suggestion was the area minus 1/4 of the area. And the second suggestion was multiply the area by 3/4. And then we also had 0.75 times the area. And with a little bit of thought, you should be able to factor the A out here, right? And if you factored the A out, you would have 1 minus 1/4 times A. Probably distributivity is the thing you want to use every possible instance in the classroom to reinforce, because people are just really shaky on pulling out the A and then putting back in the A and seeing those as the same. Once you're here, it's easy to see that it's 3/4. Okay, so that's sort of what my second term should be. So I write A2 equals what? If I was going to do it recursively, what would I write? This is sort of a recursive definition, you're telling me.
Well, do we start with the total area that we already know?
Yeah, like I don't even
Well,
know
well,
what the
so-
initial area was.
I thought we calculated the initial area as A1. Yeah?
Yeah, so the initial area is 1/2 times 2 times the square root of 3.
Okay, 1/2 times 2 times the square root of 3.
Yeah.
Good. And 1/2 and 2
Is one.
cancel.
It's just one.
So that gives us
Just the
square root of 3.
square root.
So that's the area
See,
of
I
the
didn't
whole,
get that.
the whole shebang. Fair enough.
Okay.
So then A2 would be,
Quarter of that. Whatever that is.
it's going to be 1/4 of that initial,
So each one.
or 1/4 times A1. So that's how much area we'll have after we cut that out.
Yes.
Yeah.
So you're telling me I have 1/4 as much area after I cut that out as I had to start with.
No.
No?
If you cut out one piece, you have 3/4 of the area left.
Okay, I have 3/4 of the area left.
And the
so-
triangle represents that fourth.
Okay, so here, how much area is now shaded in green?
Oh, okay, 3/4.
3/4.
Oh, I get it, I get it.
Find that. Okay. Well, we're pretty much done, right? So now we just sort of have to glue that back in. So how much area is that?
It's a fourth of whatever A2 is.
It's a fourth of whatever A2
It's
is.
a fourth of 1/4 of the original area.
The fourth of 1/4 of the original area. Okay. So it's a fourth of a fourth of the original area.
Is there 16?
Okay, so this sequence is basically areas, right?
Mm-hmm.
Okay. So, what do we?
I'm confused about what you're computing. Are you looking for the whole area after the triangle's cut out, or are you looking at the area of the triangle that's being cut out?
Well, that's a great question.
I don't know what we're
So
trying to find.
that's why I titled this area. This is actually the area
Of
after
which?
cutting out
Okay.
that's actually the area of the whole thing. This is the area shaded in green after having cut that out.
Okay, so now you're looking for it.
So,
Are you looking for the area that still exists, or the area?
well, if we're going to do this sequence, I'd have to do the area that still exists. But maybe that's not what I want to do. Maybe I want to go back and change what my sequence is.
Yeah, because if you just kept it triangle within a triangle within a triangle, you could just keep it 3/4 all the way through.
And that would be good because what we're trying to do is fit it to the tool that we have. Okay, so, sounds good. So we're going to, plan B. Okay, so what's plan B?
I guess you're not looking so much for what's being cut out or what's staying, but you're looking at the triangles, the areas of the triangles.
Okay,
As if they were just being overlaid on top of each other.
okay. So area of new triangle, say?
Yeah.
Okay, so area of new triangle. Area of new triangle. Okay, so the first time around, what's the area of that brand new triangle? You cut it out.
It'd be
Square root of 3.
square root of 3.
Square root of 3. Okay, square root of 3. Good deal. Okay, so what are we going to keep track of before? I really ought to do these sort of color coordinated. I've got this in green, right? So here's green. We can pretend like it's Christmas. Okay, then?
And then the triangle that's cut out is
Okay.
1/4
Then,
of the square root of 3.
then somehow I've got this piece that I'm cutting out.
Yeah.
So the new triangle, A2 is
So 1/4 of the square root of 3.
1/4
So,
square root.
so would it be square root divided by 4?
So, now, okay. So then what should we do from here?
A3 would just be 1/4 of 1/4 of the square root of 3.
Okay.
So you just take a fourth of the previous.
and you're saying 1/4 of the previous one, so 1/4 of A2. So by that logic, sort of what's the nth one?
1/4 of a n minus 1.
1/4 of A n minus 1. Now that is a recursive definition. What kind of sequence do you think this is?
I think it's a geometric.
Okay.
Is 4 the
Geometric.
common ratio, or 1/4 the common ratio?
Okay. We have a hypothesis that this is geometric, and 1/4 is the common ratio. So how would you get that? Well, you could, if you didn't see that this times 1/4 gets you here, you could take this, always divide it, divide A2 by A1, and this always has to be A2 by A1, has to equal A3 divided by A2, and so on. Okay, so I'm buying that, so how would you write the nth term in closed form?
AN is equal to A1, which is the square root of 3,
A1, okay, square root of 3,
times R, which is 1/4,
times 1/4,
exponential parentheses n minus 1.
Okay. I like that. So we could check sort of, okay, if I put in a 1 here, I'd have 1 minus 1 is 0. 1/4 to the 0 is 1. So I'd have square root of 3. If I put in a 2, A2, we're going to have a power of 1. So that's 1/4 times root 3. Looking good? Okay, well, so I just add all these up and then I've got the error.
No, because it's a geometric sequence that keeps going. So we need to use a formula for an infinite series.
Okay, so it's a geometric sequence, and you're saying that it keeps going, so we're going to use an infinite series. So I'm just going to add all these up, right?
Yes.
So n equals 1 to infinity of square root of 3. Yeah?
Agreed.
Okay, so what do we get here?
I'm not comfortable with that notation. Can you explain that?
Oh,
I see
yeah,
the sigma.
sure.
I understand
Okay.
that. We got the infinity.
So the sigma says, I'm going to add this to itself over and over again. So sort of, this is shorthand for, let's see if I can cram this in here, the square root of 3, 1/4, to the 1 minus 1, put in a 1 for n, plus the square root of 3, 1/4, 2 minus 1. You've got to count up this sigma, it's Greek for sum, plus square root of 3, 1/4, 3 minus 1, plus, now normally when we use this, I should say initially when we use that, it stops at 7, and so I'd finish when I had a 7 there. When it goes to infinity, it goes on and on forever. Incidentally, if you described for me a geometric sequence here, so if I added those terms together, I could even add infinitely many terms as long as what is true. Do you remember? So geometric
R is greater than
sequences.
1.
No, R is
Less than 1.
R is less than 1. So I need to be, my terms that I'm adding together need to be getting smaller and smaller.
Yeah,
But as
which is-
long as, let me just be technical here, the absolute value of the ratio is less than 1, somehow we're getting closer and closer. Sound good?
Agreed.
Is that satisfied with the sequence? So we're going to add all these terms together, we get this, and we come out with
S equals A1, which is the square root of 3,
yes, A1, so square root of 3,
over 1 minus R, which is 1/4.
1 minus 1/4. So that's, let's see, the square root of 3 over, if I have 1 minus 1/4, that's like 4/4 minus 1/4, so that's 3/4. How do I divide by fraction? Well, I would invert and multiply, right? So that's now 4/3 square root of 3. Isn't that great? Well, you might think that things are going a little too well. How much area was the original triangle?
Square root of 3.
Square root of 3. And I would encourage you to force your students to use number sense. Number sense is probably the most lacking thing among freshmen that I get in college. You ask them, if you put money in the bank and you wait 10 years, how much are you going to get? And they'll give you numbers that are either sort of less than what they started. It's sort of like, can I keep your money for 10 years and give you that class? Or like they put in $100 and they get out like a 1 with 87 zeros after it. It's sort of like, you really don't quite understand. You know, so number sense. Now, is this reasonable? How does that compare to this first number?
It's more.
It's more. That's
Well,
a problem.
isn't it supposed to be?
Well, but somehow we cut out.
You can't
So
have
I don't have as much as I had to start with. This is not shaded for a reason, right? That actually is physically not a shade. So,
Well, it's
so we're
because-
really close. I'm not wasting your time here. Or you're not wasting my time, I should say. I don't think you're wasting my time. You better not be wasting my time. But what?
It's because we were taking the
Okay.
area of, we weren't subtracting the area that we lost.
Oh, okay. So how do we fix that?
You have to subtract the area you lost.
Okay, so not all of these numbers are created equal, right?
Yeah.
This one's on the good side of the force. This is adding construction paper. What about this one?
It's taking a...
It's on the dark side of the
So,
force. So we need to sort of go back and we need to say this is actually minus.
so you would alternate your negatives.
Ah, yes, but this is on the light side of the force and the dark side of the force. So how does this change if we're doing this recursively? How would one term depend on the next term?
Well, if you put in a negative before the 1/4, you would times a negative, and that would give you a
Okay.
positive, negative, positive, negative.
Yes, yes. Math is that only place in the world where two wrongs make a right, right? So it doesn't matter that this is bad, you just negate it again and it becomes good. So in a math class, and only in a math class, if you accidentally slap somebody on one cheek, you just slap them on the other one really fast. And it's sort of like, it's all good. Yes, everybody good, besides me. I don't know why, because I don't want to get slapped around. Okay, so that's my recursive definition. So what actually comes out here?
The negative?
Negative 1/4. Your common
Negative
difference would be
1/4.
negative.
Okay, so we have, notice how close we were really to what we're doing. But this is now really, we're on the right track. Okay, this is now my geometric sequence representing, I'm adding some, I'm taking some out. I'm adding some, I'm taking some out. Notice that wasn't just a pointless comment I made about the ratio needs to be what in order for the sequence to converge?
Less than 1.
The series? No.
Absolute value of less
The
than 1.
absolute value of the ratio needs to be less than 1 in order for the series to converge. That's relevant here because, in fact, if it were, say, -5, that would mean somehow you put some in, you take out a whole lot more, you put back in even more, you can see how that wouldn't converge either, right? But because I put some in, I take out a little less, I put in a little less, you sort of getting closer and closer to the same thing. Okay? So that's where we are. We put in our negative here. So it's really surprisingly similar. This formula is very similar, except for now we're adding and not subtracting. So let's go back to here. Somebody help me out with what I have here. I have square root of 3 on the top. At the bottom I have
5/4.
5/4. Invert and multiply. And I get
4/5.
4/5. Now is that reasonable?
Yes.
Good. That's a little less than the area you started with. And that's actually what you could see if you repeated this pattern. It's somehow a little, less than that. But if you took out 1/4, if you took out a whole fourth, it's a little bigger than that. So this is a little bigger than 3/4. Right? We agreed that just the greens, that adds up to 3/4. It's a little bigger than that. And you could sort of follow that pattern. You're sort of honing in on that middle number. Okay, so I think that's a great place to stop. Good work, team.